One of the universe's most striking and most violent events is the supernova. At first thought to be the creation of new stars, supernovae get their name from the Latin nova stella, which means new star. So what are supernovae? Supernova is simply an exploding star. Supernovae experience a sudden increase in luminosity, then quickly fade again. There are two types, Type 2 and Type 1a. Type 2 supernovae result from the collapse of a massive star's core, and Type 1a supernovae involve a binary system in which a white dwarf receives transferred mass from its companion star until the accumulation of mass exceeds the Chandrasekhar limit. In nova events, stars do not surpass the Chandrasekhar limit, and the star is left intact. And in these events, they can take place multiple times on the same star. However, in supernova events, stars do surpass the Chandrasekhar limit, and nothing is left behind after the explosion. As you can see, the white dwarf's gravitational pull is strong enough to ingest the red giant's excess matter. This ingestion causes an accretion disk to form, ignite, and send the star into a nova transformation.
Type 1a supernova. After multiple transitions into a nova, mass increase sparks the carbon detonation of a white dwarf star's core. This star must belong to a binary system with a massive star in order to become a nova and then explode. The star's proximity allows the red giant's matter to fall into the white dwarf's orbit. The matter increases the white dwarf's mass and its production of thermal energy, reigniting the core's fusion of elements. The increase throws off the star's gravitational and thermal equilibrium. After the star reaches a density of 1.4 solar masses, it produces a gravitational pull strong enough to outweigh the electron degeneracy pressure, stabilizing the star. The core finally begins to collapse, and in just a few seconds, fusion spreads throughout the destabilized star, ejecting its planetary nebula through a supernova explosion. After the white dwarf has exceeded the Chandrasekhar limit and begun carbon fusion, the reaction spreads almost simultaneously. The star detonates and leaves behind its nebula. In a Type 2 supernova, after hydrogen, deuterium, helium, carbon, and oxygen have fused in a massive star's core, it begins to fuse iron. Iron, however, uses the core's energy through fission and therefore does not produce thermal energy. As the iron content grows, the core shrinks, and it creates an imbalance between the gravitational pull of the star and its production of thermal energy. The core's density then joins the protons and electrons to yield powerful neutrinos in a process known as photodisintegration. As soon as gravity breaks its equilibrium, the core will collapse and pull all matter inward at an extremely high speed, a fraction of the speed of light, with help of its gravitational pull. Simultaneously, a shock wave created by the iron core's collapse collides with the falling matter. The energy from the wave slows the material down until the core's neutrinos escape compression and blast the star's layers into a supernova explosion. The eruption sends the unburned star's gas, as well as the elements formed by its core, into space. The energy produced from the collision is demonstrated by the green gas that fills the core and its pull. The yellow gas demonstrates the amount of neutrinos formed after the collision when quantum physics takes place in the core. After compressing all its energy, it finally escapes the core and blasts the star's remaining layers into space in a Type 2 supernova explosion.
So what's after a supernova? After a supernova, the remaining core may become a pulsar, a neutron star, or a black hole. In addition, a supernova leaves behind supernova remnants, which undergo three stages: free expansion, the adiabatic phase, and the radiative phase. Super remnants are then recycled, aiding in the formation of new stars and planets, as well as many other materials such as gold, silver, and uranium.
Thank you for watching.